Hello, in this video I'll be going over how to implement greedy meshing into a voxel renderer. So I'll be talking about what greedy meshing is, how to use bitwise operations to optimize it, and how to handle storing voxel data such as the type of the voxel or ambient occlusion information. So this is how meshing works in a voxel game. You generate two triangles for each of the exposed voxel faces. And inside of each of the vertices, you would store the vertex position, the UV coordinates, and the voxel type. This is typically stored as an index into an array of textures. So I could have a red wheel texture and a green wheel texture in an array, and then index 0 would be the red wheel, and then index 1 is the green wheel. This is quite a wasteful way of meshing though, because it generates a lot of triangles. So grid meshing is a more optimized way where you merge adjacent faces together to generate bigger quads. So this is how greedy meshing, the algorithm is implemented. Instead of considering 3D mesh, that's quite complicated. So we can simplify the problem to 2D by considering each slice of the chunk individually. So first we'll consider this quad here, then this face here, and then that's all the slices of this axis. So then we go over to the next axis and consider these quads here, and finally the last axis, which is this quad here. We represent all the voxels inside the slice of the chunk as cells in a grid, where these green cells mean that a cell is present. It doesn't matter what type of voxel it is, and the white ones mean it is empty. The first thing we do is go to the first column, and we figure out where the first present cell is. And then we keep going up until we meet an empty cell to calculate the height of the quad. And then we keep checking the cells to the right of it, and if all of them are present, then we can expand the quad into that cell. So this generates a 2x4 quad. And then we set all these cells to empty so that we don't include them in a second quad. And we repeat the algorithm. So we go over here, we don't find any. So we go to the next column, still don't find any. So we go to the next column, and then we start the algorithm again from here. This can be optimized using bitwise operations, which is called binary greedy meshing. So basically, the idea is we represent each cell as a 1 or 0, and we use a 64-bit unsigned integer to represent a column. This is for 64 by 64 by 64 chunks. You would use a 32-bit integer if you wanted a chunk size of 32. The two main operations we're going to be using are bit scan forward, which returns the number of trailing zeros in a integer. So here there's 2 trailing zeros, so it returns 2. And bit scan reverse, which is basically the opposite. It returns the number of trailing ones, so there's 1, 1, 1, 1, 4. If you're using C++, then you can use the count R0 and count R1 functions, which are in the bit header. If you're using GLSL, you can use the find LSB function for bit scan forward. There isn't a function for bit scan reverse, but you can just pass in the not of the parameter, and that will give you bit scan reverse, because all you're doing is flipping the bits, and then you count the trailing zeros instead. One important thing to note is that find LSB 0 is equal to -1, where actually if it was bit scan forward, it would be equal to 64. So you do have to have a separate case for that. So this is how the binary greedy meshing algorithm works. It's very similar, but we're just using different ways to figure out the quad position and size. So first we apply bit scan forward to the first column to get where the quad starts, which, as you can see here, is 4 because there's 4 trailing zeros. So the quad starts at index 4. And then we shift the column down so that the cell we found is at the bottom. So we shift it over by the position 4. And then we apply bit scan reverse to count the number of trailing ones, which gives us 2, and that gives us the height of the quad. The next step is to generate a bit mask. So what we do is 1 shifted over by the height minus 1, which in our case comes out to 0B11. For a height of 64, we would just use the bit mask uint64 max. That's because if you're shifting 1 over by 64, then you're going to cause an overflow. And even though you subtract 1, you still overflowed, so you would get the wrong number. Well, you'd be invoking undefined behavior. It's faster to use a lookup table than doing the maths because of this if statement here. So this is the grid we had before. And next, we basically shift the next column down by position so that the cells are at the bottom, and then we AND it with the bit mask that we just generated. And then if it's equal to the bit mask, then we can expand the quad into this column here. And we just repeat that like before to get the full width of the quad. So again, it's 2 by 4. And then we set them all to 0. We do this by before we expand, we set the column equal to the column and the knot of the bit mask shifted over by the height. And that just sets the bits contained in the quad to 0. So in naive meshing, you could store the voxel type inside the vertex, but because each quad contains multiple voxels, we can't do that anymore. So there's a few ways to get around this. The first one is separated greedy meshing, which is basically where we only mesh, we generate a greedy mesh for each different type of voxel. So first we would mesh all the grass, then all the dirt, then all the stone. As you can imagine, this is quite a wasteful way to do it because it's got linear time and space complexity. Another way to do it is using a dense array. So for our chunk, we'll upload a buffer containing 64 cubed voxel types, and then we'll use the fragment position to index into that buffer and get the type of the voxel. A way that requires us to store less data is using a hash map. I personally implemented it using a bucketed cuckoo hash table. It's not the most efficient though, and you could probably do it better. And finally, indirect is a data structure which I designed, and I found it performed better than a hash map and a dense array. So here's the profiling that I've did. I was rendering this world, which is from Minecraft, and I put it into my voxel renderer. It's a 512 by 384 by 512 voxel area. For separated greedy meshing, I just assumed there was 2 types of voxels. Well, when in reality there's probably like 50 or 100. So separate greedy meshing would actually be a lot slower than these graphs show. As you can see, the indirect buffer is the best way that I found to store these voxel data. So this is how we've normally handled meshing in the greedy mesher. First, we would generate the quad containing these 4 voxels here, and then we would generate the quad containing these 4 voxels here. And each of the vertices we would have a position, a width, a height, and some UV coordinates, and possibly some other attributes. In indirect meshing, we also maintain a voxel stack. So like before, we push the first quad, which is this 2 by 2 one here. And we're also storing the voxel index 0 because there's nothing inside the voxel stack at the moment. So we're just storing the size of it, which is 0. And then we're iterating over all the voxels inside the quad, and we're pushing their types to the voxel stack. So 1, 1, 1, 1. Where green is 1 and red is 2. And now we're processing the second quad, so we push all the vertices, and inside each vertex we're storing the size of the voxel stack, which is now 4. And now we're going to iterate over all the voxels inside it. First is 2, and then is 1, and then 2, and then 1, and we're pushing those to the voxel stack. And we'll upload the voxel stack to the GPU as a separate buffer. This is how you iterate over all the voxels inside a quad. So this will return the size of the quad in 3D space, where F is just the face, I've got it as an enum, and then I've got the width and height being passed in. And then you can use a triple nested for loop to iterate over that and do something with it. For example, pushing the type to the voxel stack. This is my fragment shader where I look up the type of the voxel. The first thing I do is convert the UV coordinates from their 0 to 1 range to 0 to width or 0 to height. And then based on how I've got my UV coordinates set up, I need to flip them sometimes. You might not need to do this. And then convert those 2D coordinates into a 1D index just by multiplying the y coordinate by the width and then adding the x coordinate. And then you can add that index that we just calculated to the start index, which is the voxel index we passed into the vertex. Thanks for watching. I'll include the GitHub link in the description, and if you want to contact me, you can email me at 95_@gmail.com, or you can add me on Discord at _95.